All right, so this is our last video, and it's going to go over the last question on the rotational dynamics assignment. And this one, what it wants to know is, given this beam right here going across, and these two support systems right here, and I'll explain what all my symbols and letters on here mean, but it wants to know how far can the boy walk out across that beam before it starts to tip over. And so what I did was, I drew my little beam right here, and then we have our two supports right here. I'm going to call this support 1 and support 2. And I'm going to call the beam, I'm going to call that little b, and I'm going to call the boy big B. And then I'm going to say that the distance that he can walk out before it starts to tip is r. And so what I did was I drew on all my force vectors. So each one of these beams has a force pointing up. It has a normal force pointing up. And so here's normal force 1, normal force 2. And then we also have to take into consideration the weight of the beam. And so I drew an F little b to represent the force of the beam, and then F big B to represent the force of the boy. And then I drew in a little dot right here to mark my pivot point. So whenever we're doing static equilibrium problems, and that means that our net torque is 0 and our net force is 0, because after all, what we're really finding is what is the maximum value, what's the maximum radius before we get a torque out of it. And so therefore we're still in equilibrium, but our net torque and our net force are 0. And when we have a net torque and a net force of 0, we can choose the pivot point wherever we want. We choose it in a way to make the problem easiest. And so for this problem, I'm going to say that to the far left over here, that if we choose that as a pivot point, that's the best pivot point for this particular problem. And so let's just get started then. So the first thing I want to do is I want to add up all my torques, set that equal to 0, then add up all my forces, set that equal to 0, and then see how I can look at those two equations and solve for the radius. And so therefore, our net torque, and then I'm going to say that any force that would cause a counterclockwise rotation is going to be negative, and any force that would cause a clockwise sorry, I had that backwards. Any force that causes a clockwise rotation is going to be negative. And the reason I do that is just because it makes more sense for this problem. Now, by the way, it makes more sense for this problem, but by the way, I can choose whichever way I want to be positive and negative. It doesn't matter. You'll get the same answer. But in this case, because we have our gravitational forces, our weights pointing down, and those are normally negative, I'm just going to keep that same convention here for our torque. Okay, well, let's see what we have then. Our net torque, well, in order to find the net torque, we have to add up all the forces and multiply them by their distance from the pivot point, set that equal to 0. Well, let's just go through them then. So force 1 is on the pivot point. That's what we chose. And it makes the problem easier because now F1 goes to 0. And so I'm going to leave it in here just to illustrate that it is still there. It's just happens to be 0. So we have F1 times a distance of 0. Okay. Okay, we can see that. F1 times distance of 0. Okay. Plus, now we have the weight of the beam. That's our next force that we're going to look at. We have the weight of the beam. And so, okay, so that's the weight of the beam. And that's given to us as 40 kilograms. And so that's 40 times 10 for gravity, because our force is mass times gravity, times a radius. What is the radius? Well, anytime you have an object with uniform density, in this case our beam, if it's of uniform density, you can assume its center of mass is right in the middle of that object. And so therefore, when we're doing our torque and we have to put in a radius, we put in a radius that's half the length of that object. And that's true of anything that has uniform density. Or uniform distribution of mass. And so therefore our radius is just 2.5. Okay, what about F2? Well, F2, we don't know what that value is. And so I'm actually going to erase this little part over here just so it's not getting in the way. We don't know what F2 is, but let's just leave it in there then, since we don't know it. So that's F2. And F2 is at a distance of 3 meters. And so that's going to be plus F2. Oh, and I forgot to put a minus right here. It should be minus because the force of the beam is going down. And then we have the force of the boy. And the force of the boy is just his mass times his gravity. His mass is 20 kilograms. And so I'm going to go minus 20 times 10 times a distance of r. That's the distance that we want to find. That's all equal to 0. We'll take a look at this equation right here. Well, this goes to 0, because that's multiplied by 0. And then we have 400 times 2.5, which is 1,000. And so let me just simplify this just a bit. So this is all equal. This is all equal to negative 1,000 plus 3F2 minus 200 R is equal to 0. We have two unknowns. We have F2 and R. So what do? Well, we have another constraint, another way of looking at this problem, which is in terms of just the forces. And so we're going to add up all the forces. What are the forces? Well, in this case, the radius doesn't matter. It's only about the forces. And so we have F1, that's positive, plus F2 minus the force of the beam minus the force of the boy. That's all equal to 0. Okay, we know what these two values are. Well, let me just bring these over to the other side then. So we have F1 plus F2 is equal to F of the beam plus F of the boy. Okay, I know what these two are. I know that the force of the beam is 20 times 10, or 40 times 10, sorry. And I know the force of the boy is 20 times 10. But what is F1 then? Well, think about what the problem is stating. It's saying, how far can the boy go before it starts to tip? So at that point, it's just barely going to be leaving this support over here on the far left. It's going to be tipping like this. And just as it starts to tip, there's no longer a contact force. There's no longer a normal force at F1. And so therefore, F1 would be equal to 0. And so if we want to solve for F2 then, so therefore F1, this is 0, plus F2 is equal to 20 plus 40 times 10. Sorry, I'm running out of room. 20 plus 40 is 60, times 10 is 600. And so therefore F2 is equal to 600. And so F2 right here is equal to 600 newtons. All right, well, I'm going to erase this just so I can plug in F2 and then simplify. Hope that makes sense why F1 goes to 0 right as they're starting to tip. And so now we're left with negative 1,000 plus 3 times 600 minus 200. I'm actually going to bring the 200 over to the other side. So that's equal to 200R. And we want to solve for R. And so, well, this is 1,800 minus 1,000. That's 800 divided by 200. That's equal to 4. So therefore, the radius is equal to 4 meters. So the boy, if our radius starts, if our 0 point is right here at the pivot point, he can go out a distance of 4 meters. He can go out a distance of 4 meters before it starts to tip. All right, hopefully that helps.